Investigating Friction, the Relationship Between Work and Frictional Forces by Casey Gerlach, Marie Camp, and Katie Stocker. Resistive forces are those which oppose the motion of an object. For our experiment, we are testing for a correlation between the frictional coefficient of the opposing surfaces and the kinetic energy and work done onto that system. We hypothesize that the surface with the highest frictional coefficient will result in the least amount of change in kinetic energy, and therefore the least amount of work done to the system. Our system schema only has the IOLAB in it, which has a tension force, a gravitational force, and a contact force acted upon it. The tension force of the weight is putting energy into the system, and the friction and gravitational forces are taking energy out. Some important physics models and equations that we use to calculate the results of our experiment are Newton's second law, the work-energy theorem, and the frictional force and coefficient formulas. We also made free body force diagrams and will be seen on the following slides. The frictional force is the only arrow that will change based on each trial, as that is the only variable we are adjusting. For our experiment, we used a 100-gram weight and pulley to move the IOLAB across 3 different surfaces: tabletop, fleece, and fur. For each trial, we kept the distance traveled, mass of the IOLAB, and the applied force constant. Using the pulley and weight gives us a constant applied force and acceleration through the trial. We performed 3 trials on each surface. We used the IOLAB software to measure the position, velocity, and acceleration of the IOLAB. From this data, we calculated the frictional force, frictional coefficient, kinetic energy, and work done on the IOLAB using the formulas stated on the previous slide. Possible errors are that there were inconsistencies in the surfaces, such as bumps between fur patches or wrinkles in the fleece, that would affect the motion of the IOLAB and give it an inconsistent velocity or acceleration. Another possible error would be misreading the data we extrapolated from the IOLAB software. An interesting phenomenon that we observed is that the IOLAB has wheels, and usually in experiments, the wheels are assumed to have negligible friction. But as our calculations demonstrate, this is not the case. The resulting frictional coefficients and frictional force we calculate are not the coefficients of just the surfaces. Rather, they are a result of the friction between the wheels and the surfaces. We kept the wheels constant from trial to trial, so our results of comparing the frictional coefficients and forces are still valid. For our first set of trials, we pulled an IOLAB across a flat table. We predicted that the table would have the smallest frictional coefficient, so a higher force will be observed and more work can be done to that system with the same amount of energy as the other trials. The work calculated using both work equations averaged out to around 0.125 joules. For our second set of trials, we pulled an IOLAB across a fleece scarf. We expected the fleece frictional coefficient to be in between those of the other 2 trials, and the average work done for this trial ended up being around 0.114 joules. For our final set of trials, we pulled an IOLAB across fur patches. This fabric probably resulted in the most amount of error, as the fur was not in a single continuous piece of fabric as with the other 2, but our resulting velocities and accelerations were not extremely off the expected value. We predicted that the fur would have the largest frictional coefficient with the smaller force and least amount of work done to the system. Our calculated average work for fur resulted in 0.029 joules. In conclusion, we found that there is an inverse relationship between the frictional coefficient and the amount of work done to the system and the kinetic energy. As shown by our graph and table, as the frictional coefficient increases, the amount of work done to the system decreases. A larger frictional coefficient indicates a larger resistive force to become overcome by the energy put into the system, work, so the system will have a smaller net force. A smaller frictional coefficient indicates a smaller resistive force to be overcome by the energy put into the system, so the system will have a larger net force.